So now that we've done this, we're going to do the error analysis, for which we're going to use the trajectory file. And for that we need to go back to the preparation program, and we go to the error analysis tab. We need to select the trajectory file, which is of course the usual folder. So there it is, the trajectory file. The thing that we want to do is we want to simply analyze it. This is a number that you can use, this is an option that you can use, but for a simple analysis it shouldn't be necessary. So let's see what happens. We press analyze. The software reads the file 3 times, that's why it says running 1, 2, 3. And then it's finished, because this is quite a small file, but this can take a very long time. If I now go here, I see that new files have been created. This is the 3-dimensional, the parameter correlation file, which we can have a look at later. This is the delta G file, so it gives the errors and the Gibbs energies. But the first one that we want to see are the errors on the trajectory, the simple 2-dimensional errors. So that's this file here. And what we can do, we see a lot of data here, but the key data is here, where we have the sum of the square deviations, or the normalized sum of the square deviations for every parameter. So if we select, for example, this column here, and again we plot it, what we get is a graph like this, and what we see is that the equilibrium constant is, this is the lowest value, which we already saw from the fit, but we should consider everything in between. Let's say approximately 2 times 10 to the power 5, where this line crosses 2, and let's say about 5.5 times 10 to the power 5, where this line crosses 2, as within error margins. And we can make, so what you see is that the error margins are not symmetric. There is a smaller error to the negative, to the lower side, and a bigger error to the positive side. We can make a similar graph for the enthalpy. We see that the enthalpy is very narrow, nicely defined, nice parabola. We could do this for delta H dilution, but this is more an optimization parameter that just stabilizes the endpoint of the titration. We're not so interested in that parameter, but we are interested in the stoichiometry, and that one is also very, very, very nicely defined. So it looks as if the equilibrium constant is not so nicely defined, but we'll have another look at that parameter right now. So I'll just save this as an Excel file. I'll close this, and instead I'll go to the delta G file. In the delta G file, there was one equilibrium constant that we optimized. So I'm going to plot the delta G for this file as well. And what we see now is that this delta G actually looks far more like a parabola, and that is pretty normal. It's normally delta G that is very well defined, nicely defined, with symmetric error margins, not the equilibrium constant. So that's good as well, and now we have our delta G as well. So we can save this file as an Excel file as well. And we have our first analysis done. It looks like quite a good fit.